Hey everyone, and welcome. Have you ever really thought about how a character in a video game finds its way around? Or how your GPS just knows the best route? Well, it's not magic, I promise you. It's actually a fundamental process in AI called search. And today, we're going to pull back the curtain and look at how AI actually thinks its way through a problem. Whether it's Pac-Man munching on dots or something way more complex, like planning your day.
Just think about something you do every single day, like getting from your house to work. You don't just magically appear there, right? Of course not. You have to do a bunch of things in order. You get dressed, you find your keys, you start the car, you drive a specific route. And that whole idea, that very human act of planning a sequence of steps, is exactly at the heart of how we teach machines to think.
And that's really the key here. When the next step isn't super obvious, you've got to plan ahead, right? You have to think about what's coming. And that is precisely what we call a problem-solving agent in the world of AI. It's not just reacting to what's right in front of it. No, it's thinking. It's considering a whole sequence of moves to build a plan and actually hit a goal.
So, that brings us to the big idea for today. A problem-solving agent is basically anything that looks at a problem and starts searching for a solution. And that process, that methodical, step-by-step exploration of all the different possibilities to find a path to the finish line, that's what AI folks call search. And trust me, it is the absolute foundation for almost all automated planning and decision-making out there.
Okay, so here's what we've got on deck today. First, we'll break down the anatomy of search. Then, we'll see how it works in the real world. We'll also talk about the difference between the map and the journey, which is super important. And we'll wrap up with what I think is the most crucial part: the art of abstraction. Let's dive in.
All right, let's get to the good stuff, the core framework. Honestly, the best way to think about this is like a recipe. Before an AI can solve anything, you, the human, have to spell out the problem for it in a really specific way. And that recipe always has these 4 key ingredients.
Okay, first up is the state space. This sounds fancy, but it's just every single possible state or configuration the problem can be in. Think of it like all the possible squares on a chessboard. It's the entire universe of the problem. Second, we have the successor function. This is basically the rule book. It tells the AI, okay, from the state you're in right now, here are the legal moves you can make. Next, you've got the start state, which is easy enough. It's just the starting line. Where do we begin? And finally, the goal test. This is the referee that asks, are we there yet? Have we won? You put those 4 things together and bam, you have officially defined a search problem for an AI.
So why go through all that trouble? Well, we're looking for a solution. And in the language of AI search, a solution is really just a plan. It's a sequence of actions, following the rules from our successor function that takes our little agent all the way from the start state to a goal state. It's the golden path, the winning route through that entire universe of possibilities we defined.
Okay, that's the theory. But theory is, well, it's just theory, right? Let's make this real. We're about to take that 4-ingredient recipe and apply it to some actual problems you probably know. You're going to see just how powerful and, frankly, universal this framework is.
Let's kick things off with a true classic, Pac-Man. So imagine the goal is super simple. Just get from one side of the maze to the other. How do we frame this using our recipe? Well, the state space is just Pac-Man's current XY location on the screen. The successor function, those are his only legal moves. North, south, east, west, as long as he doesn't run into a wall. The start state is just his starting spot. And the goal test is a simple question. Is our current XY the same as the end XY? See? Just like that, we've turned a video game objective into a formal AI problem.
Okay, but now, watch this. What if we change the goal? What if the goal is now eat all the dots? Suddenly, the entire problem definition has to be thrown out and rebuilt. The state space can't just be Pac-Man's location anymore. It's not enough information. It has to include his location plus the status of every single dot on the board, eaten or not eaten. The successor function gets more complicated too. Every move now has to update both his location and potentially the status of a dot. And the goal test? Totally different. It's not about a location anymore, it's are all the dots gone? This is so important because it shows how absolutely critical that initial problem definition is.
And hey, this isn't just for video games, not at all. Think about finding a specific file on your computer, like f211.txt. We can use the exact same recipe. The state space? It's all the files and folders on your machine. The start state? That's your root directory, like your C drive. The successor function, our legal moves, are basically just go into a subfolder or go back up to the parent folder. And the goal test is super simple. Does the current file name match the one we're looking for? It's the same powerful logic, just applied to a completely different world.
And for our last example, let's talk route finding. This is the beating heart of your GPS. Let's say we want to get from Arad to Bucharest. What's our recipe? The state space is every city on the map. The start state is, you guessed it, Arad. The successor function lets us travel along any road connected to our current city. And the goal test just keeps asking, are we in Bucharest yet? And this is what's so cool. From Pac-Man to your file system to a roadmap, once you can define a problem using these 4 components, an AI can start working on solving it. It's an incredible abstraction.
Okay, so now we know how to define a problem. But to really get how an AI solves it, we need to wrap our heads around 2 really important but different ideas: the state space graph and the search tree. The absolute best way to think about this is the map versus the journey. One is the entire world, and the other is the specific path you're taking right now. So first, let's talk about the map. That's the state space graph. This is the God's eye view, the big picture. It is a theoretical map of the entire problem. Every single possible state, every city, every Pac-Man location is a dot or a node on this graph. And every action you can take is a line or an arc connecting 2 of those dots. And here's the key. On this perfect, complete map, each state appears only once. It's the total reality of the problem. And honestly, for most real problems, this thing is so huge you could never actually build the whole thing in a computer's memory.
The search tree, on the other hand, is the journey. This is what the AI is actually building step by step as it explores the world. It's a log of its trip. It starts at a single point, the root, which is our start state. Then it branches out with every possible move. And here is the huge difference. In the search tree, you can absolutely visit the same state more than once. Imagine you drive from Arad to Sibiu, and then you turn around and drive back to Arad. On the map, Arad is just one place. But on your journey tree, you've just created a new Arad node because the path you took to get there was different. Every single spot on this tree represents a unique path from the very beginning.
So let's just nail this down. The map, that's the state space graph, describes all possible states, and each state is totally unique. It's the entire world. The journey, that's the search tree, describes the specific paths the agent is taking. Here, a state can show up over and over again. It's one single exploration of that world. So, bottom line, the AI uses the rules of the map to build out its journey, hoping that one of those paths eventually leads to the treasure, the goal state.
Okay, we've talked about the what and the how, but now we're at what I think is truly the most important part of this whole thing: the why. Why on earth do we spend all this time and effort defining a problem so formally? Well, it's because this is where the human intelligence comes in, way before any AI gets to work. And this quote from the source material really just says it all. It says, key point, considerable amount of time is spent here to abstract the search problem. And that's it. Before a single piece of code for a fancy search algorithm gets written, a human being, a developer, a researcher, has to do the really hard work. They have to look at a messy, complicated, real-world problem and somehow boil it down into that clean, simple 4-part recipe.
So here's the absolute punchline. The quality of the AI's final answer is 100% dependent on how well a human defined the problem in the first place. Think back to our Pac-Man example. If we only tell the AI to track Pac-Man's X, Y location, it will never, ever be able to solve the eat all dots problem. Why? Because it doesn't even have the necessary information to know if a dot has been eaten. All the genius, all the creative, critical thinking happens right here, in that human decision of what to track, what moves to allow, and what it actually means to win.
And that really brings us to the end. This 4-part framework, it's not just for computer scientists. It's a really powerful way of thinking about any problem. So I want to leave you with a little challenge. Think about some everyday problem you solve. It could be as simple as making breakfast or planning out a project at work. Could you break it down like this? What's your state space? What are your legal moves? What's your start and what's your goal? Because at the end of the day, the better you get at defining a problem, the easier it becomes to solve it. Thanks so much for joining me.